Welcome to Temple Eke Academy and welcome to the mathematics class. Today we'll be studying together a very beautiful topic, logarithms in mathematics. This topic affects a lot of sections in mathematics, other topics in different branches of mathematics. So this is a very important topic that will enhance your understanding of mathematics. So let's take a look at logarithms. We start straight off with the definition of logarithm. The logarithm of a number to a given base is the power to which the number is raised to obtain the number. Here, we're looking at logarithm of a number. So we write log to a given base a of the number b if this gives the value x. It means the base a raised to the power x gives back the number. This is the definition of logarithm. It implies that the base to the power x gives back the number b without the logarithm written. So the logarithm of the number, logarithm of b to the given base a, if it gives x, that means x is the power to which the base a must be raised to obtain the number b. And that is what we have here. So this is the basic definition of logarithm. And then we feature this in problem solving where we're able to transpose from logarithmic writing into index form of writing. Logarithmic writing, the form involving logarithm. Indicial or index writing, the form without the logarithm. Another illustration, if we have that the logarithm to base p of the number q is another number r, it means the base p must be raised to the power r to give back the number q. So this implies, again, that the base p must be raised to the power r to obtain the number q. All right, this is the basic definition of logarithm. Now, it is important for us at this stage to state clearly if we have the logarithm to base m of a number n, we can classify the number m and n. Okay, the m represents the base of the logarithm. It is known as the base, and then it can be different values. But the number n is known as the argument of the logarithm. Argument. The argument. So the number by the side of the logarithm is known as the argument. This is the argument. If we write logarithm to base x of the number y, it means x stands for the base of the logarithm, while y stands for the argument of the logarithm. So hereafter, we shall describe them in this term: the base of the logarithm and the argument of the logarithm. Okay, let's move on. Now we have the types of logarithms there. We have the common logarithm. Common logarithms are logarithms written to base 10. Logarithm to base 10. That's the common logarithm. For example, the logarithm to base 10 of the number 2 is a standard value. From our table of logarithms, this is the standard value, 0.3010. So common logarithms are written to base 10. The base is 10. Now, it is common practice to write common logarithms without indicating the base. So log base 10 of 2 can also be written as the logarithm of 2. And it is implied. Once there is the writing of logarithm without the base shown, it is implied that the base is actually 10. So logarithm of 5 without the indication of the base means we have actually written the logarithm to base 10 of that argument 5. That's right. And now the second type of logarithm, natural or Naperian logarithm. Naperian logarithm. This is after the name of a mathematician, John Napier, British mathematician John Napier. The natural logarithms have logarithm written to base e. Logarithms written to base e. So the base of logarithm here is e. E is the Leonard Euler's constant. Another mathematician, 2.718281828, the value of e. So we can show some logarithm base e. That's natural logarithm of t, for example, is the value 0.693. We see this in applications in science, in chemistry, in physics, and in financial mathematics also, where we talk about annuities. Okay, let's move on. And now we're going to have to review the laws of logarithm. So the operations in logarithms are based on certain laws. So we're going to review the laws, and then we're going to solve problems by referring to those. Here we are, the first law. Logarithm to any base. Logarithm of 1 in any base is 0. So once the argument is 1, for example, we have log, no matter what the base is, any base at all, general x of 1. So long as the argument is 1, the result is 0. Logarithm, any base at all, any base, no matter what it is. Logarithm to base 10 of 1. Once the argument is 1, the answer is 0. This is the law in logarithm, and we shall see this in applications, many applications. Here we have the second law of logarithm. The logarithm of a number in the same base is 1. So the base and the argument are the same. The result is 1. Once the base and the argument are the same, the result is 1. So we have log any base, so long as the argument matches the base. Here the base is the base value A, and here the argument is also a value A. Once the argument and the base of the logarithm are the same, the result is 1. This is a very simple law. For example, if you have logarithm to base 10 of 10, here we have the base is 10 and the argument is 10, the result is 1. This is a standard law we shall apply in problem solving. Same base, same number, same argument, the answer is 1. All right. Another law, law 3. The power of the argument may be dropped behind the logarithm. Very powerful law. The power of the argument may be dropped behind the logarithm. Let's have log to base A of a number P with power X on it. The power on the argument may be dropped behind the logarithm. So the power belongs to the back of the log. And this will be written as the power behind X log to base A as it is written of the number P. So the power belongs to the back of the log. Power belongs to the back of the log. We can have an illustration here. We can have a simple illustration that will combine previous laws. For example, if we have the log reading to base 2 of the number 8, for example, here we notice we can actually express it in terms of the base 2. So by doing that, we have this is the logarithm to base 2 of 8 is actually 2 to the power of 3. 2 multiplying itself 3 times will give 8. And here we are, the power belongs to the back of the logarithm. So we have this is going to be written as 3 at the back of log to base 2 of 2. And now get ready to apply another law. The argument and the base are the same here. Base 2, the argument 2, which means this combination represents 1. So if we may proceed, okay, this will be 3 multiplied by same base, same number gives us 1. And 3 times 1 will give us 3. So it's the way to apply the law. This law is, however, reversible. We must remark that now. This is a reversible law. Our step depends on what we intend to achieve in the problem we're about to solve. So the power belongs to the back of the log. In a similar manner, we can evacuate the back of the log. If we have m log base a of n, and then we intend to evacuate the back of the log, we simply reverse this log. So the number behind the log can be raised as a power on the argument. It depends on what we intend to achieve. So this can be written as log base a of n to the power n. Look at this. Now, the power belongs to the back of the log, and it means the back of the log can be evacuated so that we have the power on the argument. So this is a reversible law. We can move in that direction. Yes. And we can also move in that direction. It depends on what we intend to achieve in any problem we're solving. Let's move on to the next law. Here we are, law 4. The sum of the logarithms of two numbers in the same base is given by the logarithm of the product of the numbers in that base. This is a combination law. So we intend to combine logarithms by this law. So this is actually a combination law. The intention is to combine logarithms in a single unit. It's a combination, the first combination law, really. There is another one. So we have logarithm to the base a of an argument m, the number m, plus logarithm, it must be the same base, another argument n. We have to confirm two things here. Number one, they must be written to the same base, which means they can be combined. Number two, the backs of each of the logarithm must be free of any number. The backs of the log must be free, and now they're ready for combination. The combination is in this manner. Pick up the logarithm to that same base to which they've been written, log base a, each one of them, log base a, the other one. Pick up that same log base a, and now have the combination. The first argument, m, must be multiplied by the second argument, n. Combination is completed here. This is the combination. So we have the product of the two arguments with a single logarithm to the same base to which the initial writing has been done. Let's take on the next law. Here we are. Law 5. The difference of the logarithms of two numbers in the same base is given by the logarithm of the ratio of the numbers taken in the right order. This is the second version, of course, of the combination law. Another combination rule. Yes. This is a combination law. How to combine logarithms. So in practical problem solving, we may have the need to combine logarithms. And this law says you have the logarithm to base a of the number p, for example, minus, it must be the logarithm to that same base a of another number, for example, q. Beautiful. Now, two things you must check. Number one, the logarithms are written to the same base. It is log to base a in the first logarithm. It is log to base a in the other one. This means they can be combined. Now, are they really ready to be combined? We have to check the back of the logarithm. The backs of the logarithms must be free before combination can be done. And this means we combine in this manner. Take the logarithm to that same base a to which both of them are written, log base a and then log base a, and the combination. The logarithm, positive logarithm, log base a of p is the positive one. The positive one takes the position of the numerator divided by the negative logarithm. This is negative log base a of q. The negative logarithm, that is q in the argument, takes on the position of the denominator. That's right. So the combination is completed here. Now, we can, of course, develop some deductions from the laws we just studied, the two combination laws, the two combination laws. We can have some deductions. How about mixtures? We have log to base A of P, argument P, for example, and then we have plus log the same base A of another argument Q minus log base A of yet another argument R and minus still log to base A of the final one S. All right, beautiful. So let us look at this. The first thing we want to make sure happens is that all the logarithms are written to the same base. So here we are, same base, log base A for each one of them, as you observe. This means they can be combined. They can be combined, of course, because they are written to the same base. Every one of them has log base A. Now, the next question to answer is, are they really ready to be combined right now? And we have to check the back of the logarithms to confirm this. The back of the logarithms must be free of any number. All the backs must be free. And now, because the backs are free, the combination is in this manner. We take on the logarithm to that same base to which all of them have been written, log base A, each one of them, and then ready for the combination in the brackets. All logarithms with positive values, positive logarithm to base A of P, positive logarithm to base A of Q, will occupy the numerator. So P will go ahead and multiply Q in the numerator, being positive. Positive logarithm of P, positive logarithm of Q. So P and Q will multiply themselves in the numerator divided by, in the denominator, the logarithms negative logarithm of R and negative logarithm of S. We have it that R and S will multiply themselves in the denominator. R and S will multiply themselves in the denominator. That's why. So we have S there. That's why. This is the combination. Combination completed. So the positive logarithms multiply themselves in the numerator. The negative logarithms have their arguments R and S multiplying themselves in the denominator. Let us look at another pattern. Now here is another pattern. What if we have M logarithm to base A of the number P minus N logarithm to the same base A of another number Q, now plus R logarithm to base A of uppercase R and minus S logarithm to base A of T. What if we have this writing? We have to move now for the combination. The first thing to ensure is that we're really ready for the combination. Is it possible to combine? Of course. The same base in each of the logarithms confirms that log to base A, log to base A, log to base A all round. It is possible to combine, but the second question, are we ready to combine them right now? And the answer will be by inspection of the backs of the logarithm. And there are, of course, figures, numbers at the back of the logarithm, which means we can combine, but we're not ready right now. The backs of the logarithms must be evacuated by law. Each must go on to the power position according to our law. Yes, each number at the back of the log must take on the position of a power on each of the arguments. And this can be written as, of course, logarithm to this A of P to the power M. The M goes up as the power on the argument, minus logarithm to this A of Q to the power N, plus logarithm to this A of R to the power lowercase r, and finally minus the same logarithm to base A of t to the power s. Now all backs have been evacuated. The back of the logarithms are free. And now combination can happen immediately. Right away, notice every one of them is written to the same logarithm to base A. And that's the starting point. So take on the logarithm to base A. And then the parenthesis. Now, identify the positive logarithms. Their arguments will multiply in the numerator. The positive logarithms here, of course, the first one. The positive logarithm plus logarithm to base A of r to the power r must be in the numerator. So we have the argument p to the power m must multiply the second argument r to the power r. Now this arrangement will be divided by the negative logarithm. Where are the negative logarithms? Yes, negative, of course. Logarithm to base A of q to the power n. Negative, of course. Logarithm to base A of t to the power s. Now, the arguments also multiply in the denominator. So we have the first argument, q to the power n, multiplying the second argument, t to the power s in the denominator. And the combination is successful. Now, we're going to see this in practical problems. Let us move on. Now we're in the next law, law 6. Please, if you find this video interesting, subscribe to this channel because there are very exciting lectures on this channel. Hit the bell button so that you know when I make similar videos, and then please share this video so that you can facilitate learning in others. Okay, law 6. If a number is raised to a logarithmic power, the base of logarithm is the same as the number, then the result is the argument of the logarithm. If a number is raised to a logarithmic power, that is a power that has logarithm. The number is raised to a logarithmic power. And the base of the logarithm is the same as the base of the number. Then the result is simply the argument of the logarithm. Let's go and see this. It means if we have a number a raised to a power that has logarithm in it, and the base of this logarithm is that same a as the original number. This is a as the original number, log base a. The base is a as a number, and then we have an argument p. Don't look far away, because the base of the logarithm and the number being raised to the power are the same. This is a here, and the base of the logarithm is a. Now confirm the back of the logarithm must be free, completely evacuated. This means your answer is simply the argument p. This can be proved, of course. Now, let us look at the trap. Supposing you have p to the power log base that same p of a number m, for example, and then we sneak in a small x at the back of the log. Now there is a trap in this case. The back of the log must first be evacuated before the log can be applied. So this should give us p to the power log of the same base p, but this time around we have m with the power coming up. You can see in this case we're taking the power x up. And now, because the base of the logarithm is the same as the number being raised to the power, and with the back of the log completely free, the answer is simply that argument with its power. Yes, so simply m to the power x. Very simple. And we're going to see this in real problem solving. Let us move on for now into the next law. All right. So we have law 7. If the base and the argument of a logarithm can be expressed as the same number, it has to be the same number. Same number raised to different powers. Then the result is the ratio of the power in the argument to the power in the base. Oh, this is beautiful. Let us look at an illustration to make it easy. If we can have log base a to the power x, and we can express the argument as another a to a different power. Look at this. If we're able to achieve this writing in problem solving, such that the base is a number a to a power x, and the argument can also be expressed as that same value in the base, but with different power, then don't look far away. The answer is simply the power in the argument, the power up, divided by the power down in the base of the logarithm. This can be proved, of course. So, for example, we have the problem doesn't come in this setting. The problem doesn't come in this setting, but you have to adjust to this setting. Let us see a situation where we have to adjust the problem. Supposing I give one of the examples I gave earlier, logarithm to base 2 of 8. Let's see this. Beautiful. Now, a quick inspection shows that we can really express 8 in terms of the base 2. So we can rewrite this as logarithm to base 2, and 2 can be written as 2 to the power 1. That is correct. 8 can be written as 2 to the power 3. Now we have adjusted the problem to our taste. The base is a number raised to a power, 2 to the power 1. The argument is also written as that same number 2, but to a different power 3. Don't look far away. The answer in this case is very simple. Of course, the answer is going to be based on the power in the argument sitting on the power in the base. Very quickly and straight away, we have the answer is the power up 3 divided by the power down. 3 divided by 1, and that gives us 3 as the final answer. This is very simple. And we're going to see some examples in due course. But take note of this law. The problem doesn't come in that package. We'll reset by solving until we are able to see the same number in the base and the same number in the argument. Of course, the power in the argument divided by the power in the base. Simply power up over power down. That's right. So, okay, would you like another example to buttress this? Okay, let us take on another one to show this. Supposing I have logarithm of 32, or base 32 of the number 16, for example. Look at this. Logarithm to base 32 of 16. A quick inspection shows that we can actually express 32 and 16 in terms of the same number, but raised to different powers. Can you pause the video and think of this number? Okay, and the number is actually 2, of course. So we adjust this to our setting, where we can now write this is equal to log 32 is actually 2 to the power 5. 2 multiplying itself 5 different times. And then 16 is also 2 raised to the power 4. 2 multiplying itself 4 times. And of course, we can see clearly 2 to a power in the base, the same 2 to another power in the argument. And simply, as we have said it, the answer is simply the power up divided by the power down. So simply 4 divided by 5, and we can walk away with the solution, of course. Let us take on another law. Very interesting topic, logarithms. I know you're having a good time. Just please remember to like this video, subscribe to this channel, hit the notification bell button, and of course, share so that you can facilitate learning in somebody else. Now here we are, another law, law 8. The base of logarithm can be changed, of course. This results in a fraction involving the logarithm to the new base in both the numerator and the denominator. This is a beautiful law, the change of base law, change of base setting. Now, let's get into it. We have an original logarithm, logarithm to base a of a number p. And supposing in problem solving, we don't want to use this base a. We prefer another base x. We can change the base, of course, easily. Anytime the base of logarithm is changed, there must be a fraction resulting. That is a very important point to note. So note this in your writing. Anytime the base of logarithm is changed, the result is always a fraction. So let's set up the fraction. Fraction involves the numerator and the denominator. Now your new base, logarithm to base x in the numerator divided by logarithm to the same base x to which you want to change So it is your choice. You choose the new base you want in every problem, depending on the structure of the problem. We have a new base x, a new base x. Now, based on their orientation, take a look. The argument is somewhat oriented upwards, while the base is somewhat oriented downwards. And they will take on this same orientation in the new writing. So P takes on the position in the numerator, while A takes on the position in the denominator to set up the new logarithm in our new base. Beautiful. All right. So as you can see, a new base entirely, base x, is set up. But the numbers, the arguments, and the base take on the orientation in the numerator and in the denominator respectively. Let us take a look at another one to buttress it. Supposing we have again logarithm to base m of the number n. And now we desire to have base a, for example. We can write this easily. So let's go. Logarithm, a fraction must result, of course, to the new base a we want or we desire over log base a that we desire. So anytime we change base of logarithm, a fraction must result. Now, study their orientation. The argument, of course, being somewhat directed upwards, takes on its position in the numerator, while the base in the writing, directed downwards, you can see, takes on its position in the denominator. And a new logarithm with a different base is born. One question in your mind right now is, how do we know the base to which we change logarithm? How do we know the base to which we change? How do we know the new base we want to change into? The arrangement of the problem and our intention in the problem will dictate this. And then just wait for some examples so that we can answer that question together. All right. A new law, law 9. The reciprocal of a logarithm is equal to a new logarithm with the base and the argument of the original logarithm interchanged. It's a very beautiful law. Reciprocal, which means the denominator is actually reciprocal. The denominator is the numerator rather is 1. Reciprocal of a logarithm. So we have 1 divided by logarithm, for example, to base a of p. This is the reciprocal of the logarithm, 1 over log base a of p. We can write a new logarithm. And this law says it is a new logarithm entirely, a new logarithm with the base and the argument simply interchanged. You can see that. Which means write a new logarithm, but that which was the original base a becomes the new argument. And that which was the original argument becomes the new base. And interchange. The new logarithm is born, no longer a fraction, but a pure number standing. That's right. So make another example to buttress it. If you have 1 over log base x of y, you can simply say this is a reciprocal of a logarithm, 1 over. So rewrite a new logarithm, interchange, simply interchange. Y goes as the new base and x takes the new position. Beautiful. Let us go on. Another law. And now, okay, time for us to really engage in some practice. So, illustrative examples. Are you ready? Now you can take a moment to review the laws you have learned because we're about to apply them in practical problem solving. So come with me. It's going to be exciting. Let's go. All right, here we are, our first example for the day. Here we are, our first example. So, let's get into it. We want to simplify log to the 10 of 16 divided by log to the 10 of 8. And straight away, we study the problem carefully. The same base 10 in the numerator and in the denominator. Observe that. Number 2, any relationships? Can you think of any relationships between 8 and 16? Is there a number we can raise to different powers? Of course, 16 is 2 to the power 4. To multiply itself 4 different times. And 8 is actually 2 to the power 3. So we can rewrite this already. Problem solving begins with a rewriting log base 10 of 16 2 to the power 4 divided by log to base 10 of 8, which is 2 to the power 3. Beautiful. Now, inspect for that. We have something similar. So apply a law now. The power in the argument belongs to the back of the log. That's one of the laws we reviewed today. You remember? So take each power behind, and what do you have? This is going to be numerator becomes 4 log to base 10 of 2 divided by the same thing. Take the 3 behind, 3 log to base 10 of 2. And what do you observe? The logarithm to base 10 of 2 can be struck out, being common to the numerator and the denominator. So dividing both the numerator and the denominator by the logarithm to base 10 of 2. And simply finish it off. 4 divided by 3, our final answer. Or do you prefer the mixed form? One whole number, 1 over 3. Very simple. That's right. Let's take on the next problem. All right. And the truth is out of the way. Okay. Beautiful. This is another one you can see. So we can already anticipate the combination rule here. Can you see that? In the numerator, you have log to base 10. Log to base 10. That's it. Log to base 10. And in the denominator, you have something similar. Okay, let us combine the numerator. Let's do the combination rule because we have log base 10 in each case, and the backs of the log are also free. Combination is ready. So log to base 10 of the combination. Remember, because of the minus in between them, we're coming up with a division. So 16 divided by 8. Of course, the numerator is combined. Now divided by log, the same log to base 10 in a similar manner. Since it's a subtraction, we have 4 being divided by 2. Take a moment to simplify the numerators, the argument in the numerator and the denominator. 8 can divide. 8 divides into 16, that gives us 2. And of course, 2 divides into 4, sets up another 2. And this writing can be log to the same base 10 of this time around, 2 margin up, divided by log base 10, same thing, 2 margin. And now you have the numerator and the denominator exactly the same. So division gives us 1. Log base 10 of 2 cancels log base 10 of 2, and now we have 1. Very simple. Let's proceed. So we have a lot of examples to facilitate learning. So mastery is by practice, really. You have to do a lot of examples. Let's see another one. Look at that. Evaluate. Log base 1 over 8 of 32. Log base 1 over 8 of 32. Let us think for a moment. We can see a relationship already. 8 and 32. Something can happen there. We can raise 2 to different powers to get 8 and 32. And that is the real way to go. So this is going to be, let's write, log base 1 over 2 to the power 3, writing it as 2 to the power 3 now, of 32, and writing 32 as 2 to the power 5. Yes, 2 multiplying itself 5 times gives 32. This is beautiful. Now take a moment to apply the law of indices here. The law of indices that says any number to the power fraction means that number to power negative. You have that 1 over a to the power x is actually a to the power negative x. 1 over a to the power x is actually a to the power negative x. This is the law of indices. And you need to watch another video I've made on indices as a topic. So you have to study that lecture before you can actually understand this perfectly. So let's go. Now we can rewrite by applying that law. So this is going to give us log base 2 to the power negative 3, applying that initial law of 2 to the power 5. And this is one of the laws we studied today in our lecture. Because of this lecture, we've seen this. So the base has 2 in it. The argument has 2 to different power. 2 to the power 5 up there. So simply, this is the power up divided by the power down. The power up 5 divided by the power down minus 3, which we can write more appropriately as minus 5 over 3, our final answer. Or do you prefer the mixed fraction? Negative 3 divided into 5, 1 whole number. The remainder 2 over 3, our final answer. Very simple. All right. So let's take on the next example. That's right. And take this to beautiful. This is another one. Log base of 27 of 1 over 81. Right. A quick inspection shows that we can actually write 27 and 81 in terms of 3 to different powers. Can you figure it out? Take a moment to do that. Okay, here we go. This can be written as log 27 is 3 to the power 3. And then look at 1 over 81. We can take a moment to say 1 over 3 to the power 4. 81 is actually 3 multiplying itself in 4 places. Beautiful. That same law of indices, can you remember? 1 over a to the power x is simply a to the power negative x. Do you remember? We're going to apply that right now. So this can be written as log to this 3 to the power 3 again of now clearly 3 to the power minus 4. And look at it, another law. Remember that beautiful law? The base contains 3 to a power. The argument contains 3 to another power. And simply, one strike, power up divided by the power down. Yes, the power up divided by the power down. So you have, of course, the power up, negative 4, divided by the power down, which is 3. That's right. And that gives us our final answer. Very simple. That's right. Very simple. Okay, let's move on into the next. Example 5. Let's see. Now, look at the spread. So what are we going to do for this? Of course, can you anticipate the combination? Let's go ahead. Let's get into it. A quick inspection shows that these logarithms are written to the same base. Observe this 10 there. Can you see that? Observe this 10. Observe this 10, which means they can be combined. They can be combined, of course. Now, are they ready for combination right now as it stands? A quick inspection of the back will answer that question. Look at the back of the log here. You have this figure 3, which needs to be taken away from here. So combination is not set. The back here is 3, but we have to do something to that. Let's go. What is the log? Can you remember? The back of the log can be evacuated. Simply, the number at the back is set up as a power on the argument of the logarithm. So we have this is log base 10 of 2 to the power 3 minus log base 10 of 24, now plus log base 10 of 30. Beautiful. So combination is ready now because the backs of the logs are now free. But you can take a moment to write the exact value of 2 to the power 3 before the combination. So this is going to be, take a moment. There's no need to rush it. Log base 10. E to the power 3 is actually 8 to multiply itself 3 times. And we have minus log base 10 of 24. Finally, plus log base 10 of 30. That's right. Now, combination. Let's go. Remember the combination pattern. Remember, log to base 10 will be taken because all of them have log to base 10, as you can see. As you can see, log to base 10. The first thing you want to write is that same base, log to base 10. Now, open the bracket. Ready for the combination. Those with positive logarithms multiply in the numerator. Log base 8, that's positive. And log base 10 of 30, that's positive. So we're taking 8 multiplied by 30 in the numerator. This will be divided by the one with negative logarithm. Negative, this one. You can see the sign clearly. So 24 goes downwards. And now, a reduction by division of with common factors. Let's go. 8, very quickly. divides into 24 3 times. And of course, you can see clearly 3 divides into 30, 10. So the new writing becomes log to the 10 of 10. And this is a law, the second law you started with in this lecture. Same base, same argument. And the answer is clearly 1, according to law. Review law 2 to understand this. Very simple. Let's take on the next example. So this is very interesting, right? Beautiful. Combination. The next example also shows us another combination example. Let's see. Let's take a look. Example C, another round of combination, as you can see. Let's go. Here we go. Now, a quick inspection. What do you see? What do you notice here? Of course, we need to take care of the back of the logarithm here, as you can see. All of them are written to the same base, the 10, all round. So let us take a moment to do that. Of course, the 2 moves as a power up there. And of course, you can evaluate that quickly. So this is 3 to the power t, log base 10 of 3 to the power t. You're thinking of 9 already, you're correct. Minus log base 10 of 12 plus log base 10 of 4 over 3. Now, don't be disturbed. The complex position here is nothing, really, nothing. We're going to treat it as normal value. So, and that's why you have to be objective in problem solving, maintain application of your rules, and don't be moved by the structure or arrangement of the problem. Okay. Now, let's take a moment to evaluate 3 to the power 2, and that's 9. 9. So we go. So instead of writing a new line, I can just replace with that value. Let's replace with 9 there. Yeah, let's just replace with 9. So we can save the time for writing. Let's go. 9 is the value. 3 squared is 9. Now combination is ready. Let's go straight away. Same base 10 all round. So let's take that logarithm to that same base 10. Logarithm to the same base 10 of the ones with the positive logarithm must multiply in the numerator. So let's say 9 multiplied by 4 over 3 in the numerator. Now divided by, let's have the denominator, the one with the negative logarithm, of course, 12 in the denominator. And now let's simplify this. Let's get this 3 out of the way. 3 can divide into 9, so we have 3. And that resulting 3 can divide into 12, that's 4 times. And now, what does this mean? We have log to base 10 of, in the numerator, surviving figure there is 4. Divided by, in the denominator, of course, 4. And once again, 4 can divide into 4, leaving 1. So this is log to base 10 of 1. And this is our law 1, really. Logarithm to any base of 1 gives us 0 at all times, no matter what the base is. Beautiful. Very simple, right? So once you apply your laws in logarithms and you follow the process, you definitely get the answer. That's right. Okay, let's take on the next example. Example 7, of course. All right. Now we're in the realm of standard logarithms. We're given standard logarithms in the problem. For example, here, log base 10 of 2 is given to us as 0.3010. This is standard from the table of logarithms. Log base 10 of 3 is also given to us as 0.4771. Standard. And we're now asked to evaluate log base 10 of 12. Now the strategy is to simplify this argument, 12, such that we have the given standard 2 and 3 resulting. So how can we express 12 to contain 2 and 3, or numbers related to 2 and 3? Let's go straight up. So take a moment to think about 12. Let's think about 12, log base 10 of 12. Let's think about the number 12. So I will rewrite log base 10 of 12. 12 is actually 4 multiplied by 3. Yes, of course. With lots of practice, naturally you'll be trained to understand the relationship between figures easily with practice. Practice does that. All right, let's go. So let's think of, okay, we've achieved is part of our aim. 3 is already showing here. Can you see that? The next number to deal with is 4. How can 4 be written in terms of index form to contain 2? Easy. That's easy. So we have log base 10 of 4 is actually 2 squared. Now multiply by 3. And now you can see the reverse of our combination law. We have to reverse this now. This is from an initial writing. Combination law, we can say this is distribute the log within to both of them, log base 10 of the first number, which is 2 squared. And because we have times in between, you can say plus log to base 10 of 3. Beautiful. So you must learn how to do this. Yeah. When you have times in between, the individual logarithms, we have themselves separated by the plus. That's why. So the next law, apply the law that says the power on the argument belongs to the back of the log. And now by writing that, we have in the next area, this can be, if I have a demarcation very quickly, so I can have that. All right. And this is going to be equal to 2 at the back of log to the 10 of 2. Now plus log to the 10 of 3. And by substituting the values given to us, you can see log base 10 of 2 is 0.3010. We can facilitate the solution. To multiply by the value of log base 10 of 2, 0.3010, plus the value of log base 10 of 3 is 0.4771. Take a moment to do this multiplication. To multiplying everything you see here, that is 0.6020 plus now 0.4771. So addition of decimals is by equivalent digits in equivalent positions. 4 figures after the decimal point, which means they are set. 1, 2, 3, 4. 4 figures after decimal point, they are set. The last signal here, 1 plus 0, which is 1 at the end. 7 plus 2, 9 at the end. And of course, 7 plus 0, 7. 4 plus 6, 10. 10, write a 0 and spill over the 1 to the other side. 0 plus 0 plus the incoming 1, 1. And that is our final answer. Very simple. So the high points again, ability to recognize the splitting of 12 to contain numbers in terms of 2 and 3. Then a reversal of the combination law, where you have the logarithms separating them out. Now, substitution of the standard values given. 0.3010 for log base 10 of 2, and 0.4771 for log base 10 of 3, and the final computation. Very simple. Let's move on to the next example. More on combination. Beautiful. So the challenge here in this problem is the presence of the decimal point. So this example is designed to show us how to handle the position of the decimal point. Let's go straight up into it. We have log base 10 of 0.54. First, change this into a fraction. From decimal, move into fraction. So you have log base 10. To change the decimal into fractions, in one of my videos, the topic fraction was dealt with, so you have to find that video. This is 5, 4. You write the significant digits, which is 5 and 4, and place this on 1. And then find out how many digits are there to the right of the decimal point. 2 of them, of course. 1, 2, which means you have 2 zeros here. Beautiful. This needs to be simplified further. Anytime you have 100, 1,000, or related figures to the base 10, there's no need to do any cancellation. For example, 2 can divide into these figures, but there is no need to do that. So do the retention. Now we're thinking of how to split 54 into numbers containing the given standards 3 and 2. How do we do that? So this can be written as log to base 10 of 54 is actually 27 multiplied by 2. A quick division can help us see that. On this side, if you decide to divide 54, divide by 2 immediately. You have 2 divided into 5, that's 2. Remainder 1 by the side there, 14. 2 divided into 14, that's 7. So 2 multiplied by 27 will give 54. All of this divided by 100. That's right. And now we can think of the 27 in terms of 3. So 2 is already available in the standard, and we need to deal with 27. So this can be written as log base 10. Can you take a moment to think? How can we break up 27 to contain 3? 3 to the power 3. 3 multiplying itself 3 times gives 27. Now times 2. Then divide by its times express the 100 as 10 squared. Yes. And now we can do our reverse of the combination law. To reverse the combination law for this, log base 10 will be given to each of these. Those that multiply themselves up will take the positive logarithm to this 10, while the one in the denominator will take the negative logarithm to this 10. Let's see that. So this is going to be logarithm to this 10 of 3 to the power 3, positive in the numerator, again, plus the same logarithm to this 10 of 2, positive also, because it is in the numerator. But now, minus logarithm, same base 10 of 10 squared, the one in the denominator. Notice how the expression in the denominator acquired the negative sign. That's basic. And now, what needs to be done? 3, the power in the argument here, brought to the back of the log by law. And this will give us 3 by the side of log base 10 of 3. Now plus log to base 10 of 2 minus the same thing. The 2 comes to the back of the log. So that we have 2 log to base 10 of 10. This is beautiful. Now it's time for substitution. We have achieved our aim. Logarithm to base 10 of 3 right there, giving us 0.4771. Logarithm to base 10 of 2, giving us 0.3010. And then logarithm to base 10 of 10, which is by law, 1, going to give us 1. Let's do the quick substitution. This is going to give us 3 multiplying the value of logarithm to base 10 of 3, given already as 0.4771. Substitute the value. 0.4771. Then plus logarithm to base 10 of 2, also given as 0.3010. So we have that 0.3010 minus 2 multiplied by logarithm to the same base as the same argument. Same base, same argument, that's 1 by law. Specifically law 2 in this lecture. Let's carry out the multiplication here. I don't want to press the buttons of the calculator for now, so let's go together. 3 times 1 is 3. 3 times 7 is 21. So I write 1, taking 2 over. 3 times 7 is another 21, plus the 2 incoming, 23. So I write 3, taking 2 over. 3 times 4 is 12. 12 plus incoming 2, 14. I write 4, taking 1 over. 3 times 0 is 0 plus incoming 1 is 1 to decimal point. That's right. And now we can, of course, add 0.3010. Now minus 2 times 1, that's 2. Once again, let us add these values with the decimal and let the 2 stand by. So let's add these values. Once again, I want to go with corresponding or equivalent digits. 0 plus the last 3 here, 3. 1 plus the 1 here, that's 2. 0 plus the 3 there, that's 3. And 3 plus the 4, that's 7. Decimal point position maintained. And 0 plus 1, that's 1. So 1.7323, now minus 2. Beautiful. Now, don't be in a hurry. This is the point where you can express the answer in a non-acceptable form. Now, 1.7323 minus 2 on your calculator will give a negative value if you do that. So we don't want that negative answer. So don't do that. Let us erase the left area of the board so that we can continue our work here. Let us just erase this for space. Let's go. So you're going to have to subtract, not using your electronic calculator, no, because you're going to get a negated answer, which we find objectionable. You have to subtract the way it is written. So the rule is subtract the way it is written. Let's go. So have them in layers. 1 point, let's go. 7, 3, 2, 3. Now to subtract the way it is written, 2.0 all the way, so that it is a decimal like the numerator, or like the one on top rather. Let's subtract. 3 minus 0, that's straight away 3. 2 minus 0, that's 2. 3 minus 0, that's 3. 7 minus 0, that's 7. Decimal point retained. And 1 minus 2 now. 1 minus 2 is actually minus 1. But we can't write that minus 1. We're going to write it as bar 1. Bar 1. So it is bar 1. And our final answer is bar 1.7323. That's it. Now, if you go to the table of logarithms, the 4-figure table, go to the 4-figure table, and you want to check the logarithm of 0.54. Number logarithm, that's the number, and that's the logarithm on the 4-figure table. And if you position 0.54 here, to use the logarithm, you have to describe this in terms of the characteristic and the mantissa. What's the characteristic of 0.54 now? By the number of zeros, of course, by 1. Then you can look up 54 under 0, and of course, you're going to get 7323. So look this up in your 4-figure table, not from the electronic calculator, and that is the acceptable answer. Very simple. We have other examples so that we can master the learning here. So let's look at the next example. Example 9. That here we have it. We have example 9. Let's take this process away so that we can go into it straight away. All right. We're given standard logarithms. Log base 10 of 2 is 0.3010. You can see that. And then log base 10 of 3 is 0.4771. Now we have to find log base 10 of 0.015. Let's get into it very quickly. Transform this into a fraction, from decimal to a fraction, and we know how to do that. We're going to write log base 10 of the significant digits. That's the digits without the chain of leading zeros. Write simply 1 and 5 in the numerator. Place this over 1 and find out how many digits in total after the decimal point. 1, 2, 3. So load 3 zeros. Of course, you're thinking of dividing by 5. Please don't do that, because the 1000, as you can see, is related directly to the base 10. Please delay the curtain, not now. So instead, think of how well we can express 15 in terms of 3 and 2. How can we do that? Okay, if we decide to really divide here, let's see. 5 divides into 15, that is 3. And 5 divides into 10, that's 2, with these 2 zeros. Okay, we can do this. We can do this because we can still bring out 100 in this number. So what do we write? This is going to be log base 10 of 3 divided by 2 multiplied by 100. Can you see that? So we're right on track. Can you see the figures 3 and 2 are beginning to show up? So let us express the 100 in the right way here as an index. So this is log base 10 of 3 divided by 2 multiplied by 100 is 10 to the power 2, 10 squared. Beautiful. And now we can use the reverse of our combination law. So break this up by the reverse of the combination law. The one in the numerator, of course, will be the positive logarithm. So log base 10 of 3. The one in the denominator, each of them, negative logarithm for being in the denominator. So minus log base 10 of 2. Another minus log base 10 of 10 squared. Beautiful. Now, let's do justice to this power, the power behind. return to the back of the log. So we have, this is going to give us log base 10 of 3 minus log base 10 of 2 minus 2, of course, log base 10 of 10. And now problem is almost solved because we have values we can easily substitute. Log base 10 of 3 is already given to us. That's it. 0.4771. So let's proceed. 0.4771 minus log base 10 of 2. Log base 10 of 2 is given to us already. 0.3010. And of course, minus same base, same number. We don't need to substitute that because this is 1. And 1 multiplied by 2 here will give 2. So we can escape with it. Now, allow the 2 to stay while you interact with it. So how can we get this through? Let us go ahead and link up this as it is 0.4771 minus, both of these are negative, so we can take them together. Look at this two. Yes. So if you take them together, that's going to be minus 2.3010. And don't use the calculator at this point because you're going to get an answer that is negative. Rather, subtract the way they stand. Subtract the way they stand. Let's go and do that subtraction here. So I have to erase this for space so that we can do that subtraction the way they stand. So subtract the way they stand. Let's do that subtraction the way they stand. So that's right. Let's go. Let's go. Now we have 0.4771 minus 2.3010. Yes. So it's time for that. Let's subtract. So 1 minus 0 gives us a 1. 7 minus 1, that's 6. 7 minus 0, that's 7. And 4 minus 3, that's 1. Decimal point, maintain. 0 minus 2. Up here, let's see. 0 minus 2 gives you minus 2, which you can write like that. And we have to change this into bar 2. So this is bar 2.1761. Once again, when you look up this value on the table of logarithms, 0.15, this will be the value. Characteristic, bar 2 point, and you look up 15 under 0, you get 1761, of course. 1761. That's right. All right. So we can take on the next example very quickly. Take on the next example now. All right. Example 10, another round of it. So let's clear the spaces. Still applying the combination. We're given log base 10 of 2, 0.3010. Log base 10 of 3 is 0.4771. This one includes log base 10 of 7, 0.8451. So let's get into this. Straight away, we have to change into the fraction mode. So this is going to give us, it is equal to, straight away, log base 10 of 42, the significant digits. Of course, this chain of zeros are not significant. So let's take on 42, but we place it on 1, divided by 1. And then how many zeros will accompany this one? How many digits, including these zeros after the decimal point? Let's go. 1, 2, 3, and of course 4. 4 zeros here. 1, 2, 3, 4. That's right. We already have figure 1 here, so we're not thinking of cutting this. Let's think of 42 in terms of 2, 3, and 7. So I can already think about that. Can you figure it out? So this is log base 10 of 42 is actually 6 times 7, right? And 6 can be split into 2 multiplied by 3. That's 6. Now multiplied by 7 divided by 10 to the power 4. Can you figure this out? Beautiful. Now we use the reverse of the combination law and spread this out. Each of them will have the logarithm to base 10. Log base 10 of 2. In the numerator, they're going to have to add, which was log to base 10 of 3. Still, plus log to base 10 of 7. Now in the denominator, minus, of course, log base 10 of 10 to the power 4. So where's the pressure point where we have to deal now? Of course, the power. This needs to come to the back of the log. And that will make us have one more line of writing. Log base 10 of 2 plus log base 10 of 3 plus log base 10 of 7. Now, minus, with the 4 coming to the back of the log, we have 4 by the side of log base 10 of 10. This is beautiful. And of course, this is same base, same number, which is 1. So 1 times 4 here is 4. Now it's time to substitute the values. Let's go. Okay. We're going to have the value of log base 10 of 2 is already given to us. Let's pick it up. 0.3010. And we have plus the value of log base 10 of 3. Log base 10 of 3 is 0.4771. More. Plus log base 10 of 7. Log base 10 of 7 plus 0.8451. And finally, minus 4. And you know why? Same base, same number. Gives you 1. So 1 multiplied by 4 is 4. Now, this is the arrangement we have. How do we deal with this? Let us add up the decimal, this 3. And then the result will face the minus 4. So we have, from the far right-hand side, all of them are written to 4 decimal places. So we have corresponding positions to be added. 1, last here, plus 1, making 2, plus 0. That gives me 2 at the back. Next signal, 5. 5 plus 7 gives me 12. 12 plus 1 gives me 13. Now write 3, filling 1 over to the next digit. Let's go. 4 plus 7, 11. 11 plus 0 still remains 11. Plus the incoming one, that's 12. So I write 2, taking 1 over. Last 8. 8 plus 4 is 12. 12 plus 3 is 15. 15 plus the incoming one, 16. All right, 6, taking over 1, decimal point position. 0 plus 0 plus 0 is 0, plus the incoming one filling over, I have 1. Now, minus 4. Look at that. Once again, you have learned in this video that you do not use your calculator to evaluate this. Rather, let us go ahead and subtract them the way they stand. In this little space here, let's go. 1. Now, let's take this away. In this little space, let's go. So we have 1.6232. 6232. Minus 4. And 4 to match like a decimal. Let's have this chain of zeros. It doesn't really change the value of the 4. Subtraction time, let's go. 2 minus 0 at the back, let's go. 3 minus 0, 3. 2 minus 0, that's 2. And now 6 minus 0, that's 6. And finally, 1 minus 4. 1 minus 4 is minus 3. Are we going to write minus 3? No, you've been through it. Bar 3. So we have bar 3. 0.6232, our final answer. Very simple. Bar 2. 0.6232, our final answer. Very simple. Okay, let's move on to the next example. Let's move on to the next example. 11, let's go. So this video is generous with examples. I want you to achieve a mastery of this topic. You learn logarithms, and that is all over with logarithms. Anywhere you come across logarithms, you are a problem solver. That's the intention. That's the intention making this video. You are a solver. Let's go. This next example, the standard logarithm is given in terms of a an unknown x. So we want our final answer in terms of x. So a very simple problem. Let's go. Given that log base 10 of 2 equals x, find log base 10 of 8 in terms of x. Let's go. Solution begins with achieving. You can see the base in the standard given is the same as the base in the problem we want to solve. Beautiful. Now, look at the two arguments. That is 2 and that is 8. Any relationship, that's a clue already. Any relationship, can you figure it out? Good. So let's take up log base 10 of 8. And now express 8 in terms of 2. That's the clue. So this is going to give us log base 10 of 8 is actually 2 to the power 3. 2 to the power 3. And now, remember, the power belongs to the back of the log. So this is going to be 3 log base 10 of 2. Beautiful. Log base 10 of 2 is the value given to us in the problem. Log base 10 of 2 is already given as x. So we're going to replace all of it with x. And that means our final answer can be written 3 with x. 3x. Very simple, isn't it? That's right. So the intention is to express the 8 in terms of 2 and then substitute log base 10 of 2 with x. Beautiful. Let's move on. The next example. Okay. So that problem, let's take this straight away. Let's go. Given that log base 10 of 2 equals x, find log base 10 of 5 in terms of x. Now, anytime you have 5 and then the base is 10, there's a special way to deal. So let's pick it up. Log base 10 of 5. Can you take a moment? How can 5 be used there? Can you take a moment to reason? This time around, not only by multiplying, you can also divide when changing figures. So 5 can be written as log base 10. 5 can be written as 10 divided by 2, of course. You can see. So that's the common trick here. 5 is actually 10 divided by 2 because the 10 is related to the base of the logarithm. So solution will be facilitated. Let us separate this out by the combination law, the reverse of the combination law. We have log base 10 of 10 in the numerator minus log base 10 of 2 in the denominator. And follow this up very quickly. Same base, same argument. You know that by law 2 in this video, 1. Same base, same argument, one whole number, minus what we're given. Log base 10 of 2. We're given log base 10 of 2, and it is f. So the answer is 1 minus f. Very simple. Now, note in this video, you learned how to change 5 when it comes to log base 10 into 10 divided by 2. So not just multiplication works, division can work in special cases like this one. All right. Please take a moment to subscribe to this channel. You're going to be getting notice when I make new videos. Very exciting videos like this one. Already you feel confident about the topic, logarithms. Anywhere you find logarithms, you are a problem solver. Let's see the next example. All right. Now, we have a times in between logarithms, and that is a challenge there. We have a time. Anytime, I make this a general rule. Anytime you have a times in between two logarithms, it is a sign that you're going to have to change the base of the logarithm. Look at it. The base of the first logarithm is 2, different from the base of the second logarithm, 3. So we're going to bring in the change of base technique. Let us get into it. This problem, log base 2 of 3. We can change base. Log base 2 of 3 to multiply log base 3 of 4. Now, we're going to change one base into the other. Let us change the base 3 on the right-hand side to become base 2. So let us leave log base 2 of 3 and move to change this base 3 into base 2. Remember, one of the laws in this video, anytime the base of logarithm is changed, a fraction must resolve. So let's go logarithm, the new base we want to change into. We want to change into the base 2 so that they are similar. Log base 2, a fraction must resolve. Log base 2, here we have it, a fraction. Now, remember the orientation. 4, looking up, occupies the position in the numerator. 3, the base, looking somewhat down, occupies the position in the denominator. And here we are. Take a look, take a look. Log base 2 of 3 can strike out log base 2 of 3 right away. Can you see that? Amazing. The problem reduces to log base 2 of 4 alone. Log base 2 of 4 can easily be written as log base 2. 2 is 2 to the power 1, or 4. 4 is 2 to the power 2. Remember this law? So the result is going to be, now I have base 2, and then I have 2 to the power. So you have this law that we have reviewed together today. The power up divided by the power down. And 2 divided by 1 gives us the final answer, 2. Very simple, isn't it? Now you're asking the question in your mind, we changed the base 3 to become like base 2. What if we change the base 2 to become like base 2? Are we going to get the same answer? Yes, of course. Let's see that. Let us settle to say the problem again. Log base 2 of 3 multiplied by log base 3 of 4. Let's do that. Now, we want to change this into base 3. A fraction will result, of course, by law. So we have our new base, log base 3, the new one, divided by log that same new base 3. Now we have a fraction. And then maintain the orientation of these numbers. 3, looking up, can you see that? We occupy the position in the numerator. 2, looking down, we maintain its position in the denominator. You have changed base successfully here. Now times right-hand side, we can write this as log base 3 of 4. And 4 is actually 2 to the power 2. Can you see that? Now take a moment to return the power behind the log by log. So this is going to give you log base 3 of 3 divided by log base 3 of 2. Now multiply by your new writing when 2 is at the back of the log base 3 of 2. Now take a moment to see what is common that can be cancelled now. In the numerator upstairs, log base 3 of 2 out. In the denominator downstairs, log base 3 of 2 out. And now the problem reduces to interpret it. Same base, same number. When the base and the argument are the same, that's our law 2 here in this video. 1, same base, same argument, 1, times the surviving figure here, which is 2. Now 1 times 2 gives you back 2 as previously obtained. So the two answers are the same. You can see that. So you're going to get the same answer whichever way you go. This is change of base technique. There is another example to buttress the learning. Please hit the like button. You need to know when I make another video on another topic. You need to know when I make another video. So hit the like button after subscribing to the channel. Let's take a look at another example. That's right. Here in the traces. Here we are. Log base 3 of 8 multiplied by log base 2 of 9. Let's go. So let me pick it up. Log base 3 of 8 multiplied by log base 2 of 9. Beautiful. So we can change one base into the other. Which base are we going to change? Anyone. Anyone can be changed into the other. So let me leave the first writing as log base 3 of 8. It's a matter of taste, choice, and style. That depends on you. So times, now I'd like to change the base 2 here into base 3, which means a fraction must result. I'll have my new base, preferred base, base 3, log base 3. So a fraction, I'm preparing for the fraction. I've changed base 2 into base 3, a fraction has resulted. Now, what will be the arguments written by the side of each of the logarithms? Check their orientation. The 9, written somewhat upwards, will take the position in the numerator, while the 2 beneath will take its position in the denominator. That's right. And the change of base is successful here. Next, let's start thinking of a cancellation. Outrightly now, you cannot cancel log base 3 of 2. Yes. So you have to make it happen. Make it happen. How can you make it happen? Are you already thinking of the 8? That's a good way to think. That's the way to go. Let's go. Log base 3 of 8. 8 is actually 2 to the power 3. To multiply itself 3 times. And are you thinking of making the 3 to come behind the log? That's the way to go, of course. So I can do that. I can do that right now. Grant your wish. Yes. Grant your wish. You want that 3 behind the log. Your wish is granted. Now multiplied by log base 3 of 9. 9 is also 3 to the power 2. Like that. And now you have asked me to send the 2 behind the log. Of course, your wish granted again. Yes. As you can see. Now divided by log base 3 of 2. And now cancellation is ready. Let's go. Log base 3 of 2 up there. Log base 3 of 2, same values. Out and out. And we proceed with the surviving figures. This is 3 at the back here. Don't forget it. That's 3. Multiplied by 2 at the back here. Don't forget it. That's 2. And multiplied by the remaining result. Same base, same number. 3, 3. Based on the argument, the same. Log 2 in this video says we should have 1 as value. Now multiply all of this together. 3 times 2, 6. 6 times 1, that's 6 as our final answer. Very simple. Now, if you like, take a moment, pause the video, and do this calculation, changing the base 3 here into base 2, while you retain the base 2 of 9 there, and see if you get the same answer. Of course, you're going to get 6 as answer. So do that, pause the video, do that calculation to confirm that you know the process. All right. Let's take on the next example. That's right. Now it's time for application to compound interest. Compound interest, we can apply the knowledge of logarithms to compound interest. So let's see one example for that. Good. How long would it take a sum of money invested at 25% per annum compound interest to increase to 4 times its original value? And we're given log base 10 of 2 is a value here 0.3010. Good. The log base 10 of 2 here is the value, standard value 0.3010. I think that should be standard in your system for now. So we're going to use that in our calculation. Let's get into it. In compound interest, we know the amount of money expected after investing the principal amount P is given by 1 plus the rate, if it is given in percent, divided by 100, raised to the power the number of years, n in this case. This is the compound interest formula, of course. And now we can reduce this formula already by looking at the value of the rate. With the rate given as 25% already, we can reduce this formula to A equals P into 1 whole number plus substitute R to be replaced by 25 because we know it's 25 divided by 100 to the power the number of years, and we're looking for the number of years here. Let me make a general rule. Anytime you ask to find a variable which is actually a power in an equation, in an algebraic equation like this, what you have to find is a power. There's a sure move of introducing logarithm to both sides. An introduction of logarithm to both sides will guarantee the solution. Observe that in pattern. So this is, if we proceed, 25 can divide into 100 4 times. And now we can write A is equal to the principal amount into 1 whole number plus 1 over 4. Take a moment to do that. Fractions. You need to find my video on fractions. 1 plus 1 over 4 gives you 5 over 4. 5 over 4. See that? In fact, anytime you ask to add 1 to any fraction, simply, a quick technique is to add the numerator and denominator together. 4 plus 1 gives you 5. Place it on that same denominator in the fraction given. 4. This is a quick technique. If you ask to add 1 to any fraction, 1 plus, let me say 7 over 9 again, another 1. What does it give you? So long as it is 1 being added, simply add up the two of them. Numerator and denominator, let's go. 7 plus 9, 16, divided by that denominator present, 9. So you can test that with many fractions. So please look for my video from this channel on fractions and study. This is to the power n. Now it's time to show the relationship between A and P. The amount of money expected has increased to 4 times its original value. The original value is the principal amount. So when the amount expected has grown to 4 times the principal amount, that's the original amount, is the principal invested. So anywhere we have A, we're going to fix in 4P in this expression. Let's go. And that is the position of A. Get ready for the substitution. It implies that we have 4P equals P into 5 over 4 to the power n. That's right. And now the P existing at the same level in the same order on both sides can be eliminated. So the result is 4 equals 5 over 4 to the power n. Let me write 5 over 4 to the power n equals 4. I have the n on the left-hand side where I prefer it now because it is the one we're looking for, the unknown we want to find. Now, can you see the power is hanging up there? Anytime what you want to find is hanging at the power, you need to introduce logarithm. So let's go. Introducing logarithm to be sent to both sides. That's a sure way to go here. Introducing log to be sent to both sides. That will guarantee the solution, of course. Introducing log to be sent to both sides, we have log to be sent of 5 over 4 to the power n must give log to be sent of 4 on the right hand side. And now let us do a quick erase to create space. Let's create some space. Let's create some space so that we can do justice to the problem. Create some space there. Let's go. Now here we are. We already have log descent 5 over 4 to the power n. Now use your power law. Bring to the back of the log. Now you have n by the side of log to the descent of 5 over 4 will be equal to log descent of 4. And now it's time to separate this by law. There's a law of logarithms we're going to apply here. You know the law, combination law in reverse. That means n attached to the result of that expression. Log descent of the first one, 5, minus log descent of 4. We then give us log descent of 4 on the right hand side. Beautiful. So this is the new face of the problem. And this is the new face of the problem. So we have now we can break this up into making n the subject of formula now. Can we do that? Of course we can. So n as subject of formula will be all of that on the right hand side. Log base 10 of 4 divided by log base 10 of 5 minus log base 10 of 4. And by solving this, we have the answer. So let's create more space so that we can solve it. Good. The solution is in D, of course. Now we have this is going to be, let me have a demarcation there. So we have n equals log base 10 of 4. We can easily have that. That is log base 10 of 2 squared divided by log base 10 of 5. We have been through that, how to deal with 5 when we have the base as 10. Do you remember? How do you deal with 5? Can you remember? That's 10 divided by 2 minus log base 10 of 4. 4 is established as 2 squared. To continue the simplification process, You have to be patient with it. Sometimes you need to be patient. Follow the steps until your answer arrives. Don't force the answer out. Let's go. This is 2. Log to base 10 of 2. Let's go. Log to base 10 of, you have 10. Now, minus log to base 10 of 2. And now, finally, minus 2 to the back of the log. You have 2 to the back of log to base 10 of 2. Beautiful. This is a new phase. Let's create more space. So you have seen log base 10 of 2 occurring, so we can combine them as like terms. Yes, of course, we can combine them as like terms. Log base 10 of 2 over there. So we're going to combine them as like terms in the next step. Log base 10 of 2. And so these are like terms. Let us take them together. Negative 1 minus 2. That's negative 3. So we have n patiently is going to give us 2 log to base 10 of 2 divided by, we have that, log to base 10 of 10, same number, already we can say it is 1, minus 2, that's minus 3 log to base 10 of 2, minus 3 log to base 10 of 2. And that implies that n is equal to 2 log base 10 of 2 over 1 minus 3 log base 10 of 2. At this point, log base 10 of 2 can be substituted because we have this value already. And don't try to cancel them out, of course, because this term, 3 log base 10 of 2, is being subtracted from 1. So this log base 10 of 2 is not able to cancel. You have 2 multiplied by 0.3010. All of these divided by 1 minus 3 into the same value, 0.3010. That's right. And now let us multiply as appropriate. 2 multiplied by 0.3010 gives us 0.6020 divided by 1 minus the result. Expand it. 3 times 0 out there, 0. 3 times 1 is 3. 3 times 0 is 0. And 3 times 3 is 9. And we have the decimal point is 0.9030 to be subtracted from 1, of course. So let's go. We have to create more space. So erase this. Erase that. All right. That's right. All right. Here we are. So in this problem, really, the log base 10 of 2 was given to 2 places of decimal. So I can drop other digits after the 2 places of decimal. So n here, it was given as 0.30 here. We have used a longer expression. So I can drop the 2 places of decimal and have 0.6020 divided by, let me subtract 1 before that approximation. Let's subtract this from 1. 1 minus all of these gives me 0. So I'm subtracting 1 minus 0. That's 0. So if I have to subtract 1.0 minus 0.9030, we have the value. So 1 has filled 10 over there. Minus 3, that's 7. 9 remaining. 9. And we have 0. And then we have this. So if I have to go and approximate this, after I have 0.970 here, I'll have n approximate to 2 decimal places both ways, 0.60 divided by 0.9030. and this gives us n is approximately 6 years. So this amount of money to be requires 6 years to 0 to 4 times its original value. So 0.60 divided by 0.10 gives us 6 years. 6 years, and that is the final answer. So that's application to compound interest. So if you see a compound interest problem, and then the time taken for investment is required, it's a sign that you're going to apply your logarithm technique of logarithm. Okay, so now it is your turn to do some practice. It's your turn. And that's the only way you can really become an expert. I've made a video on my YouTube channel. You can find it. Okay, it tells you about, it's a narration on my quote, one of my favorite original quotes. Mastery and expertise are product of persistence and consistency in practice. You have to practice. There's no other way to go. You have to practice. So I have this ready for you. Attempt all 16 questions. So attempt that. Yeah, this is the so take a moment and solve these questions. You can pause the video while you do that, and or you can go to the next. Yeah. So they're basically most of the things you've done to facilitate understanding. Don't conclude your learning in any topic without solving problems. So you're going to have to solve this problem. And this video is a powerful lecture in logarithms. It has converted you to somebody proficient in logarithms, but you need to follow it up with your practice. Solve problems everywhere. Yes. So, and then the last one. Yes. Okay. So please take a moment, solve all these problems, and now also I've prepared the answer key for you. So up next is the answer. Pause the video, solve this question, and make sure you check all your solutions with the answers. So it's an exciting time. Are you ready for the answers? So take the answers. Here we have the answers. That's right. So let's see. These are the answers. 15 of them. Now here it is. My favorite quote: mastery and expertise are products of persistence and consistency in practice. As you can see. Okay. And that's an original quote credited to me. So thank you for watching this video. This video, I'm sure it has really increased your skills, improved you in logarithm. So subscribe to this channel and follow us on YouTube, Facebook, Instagram, TikTok, and LinkedIn, of course. And you can contact me directly by sending a message on WhatsApp. You can look for some of my books on Amazon. Just go to the Amazon store and type Temple Eke and see some of my books, and you can purchase some of them. You can send me a mail also, templeakeacademy@gmail.com. Thank you for being part of this session, wonderful session. Please do a review of the content of this video, solve all the problems you have been asked to solve, and then look up the answers. And if you have any question that is not clear among the questions set, you can send a message in the comment section. You can request me to solve the problem afresh, or you can request me on any topic that you have challenges. Yes, my name is Temple Eke, and I remain yours in the drive for success in your academic work. Thank you for being part of the session again. Until I come your way next time, stay blessed. Keep your practice up. Remain solid. Bye for now.